Okay, continuing with Faraday. Let's call this fields and currents. But before I get to that, I want to finish up what I was talking about this morning. Remember, this morning I ended telling you about this supermagnet that Joseph Henry built, a 85 or 90 pound magnet that could hold 2,000 pounds of iron. And I just want to finish explaining exactly what Henry had accomplished and why he was able to build a magnet so much stronger than any magnet that people had seen before. Remember, I talked a little bit about Ampere's idea of how a magnet worked. And Ampere had the idea, if you just take so this is, okay, call this first section electromagnets. Okay, so I'm continuing that from this morning. Let's say you have a piece of iron. And you put it in a magnetic field, and I mean, you put it next to permanent magnets, lodestones, okay, and you turn this thing into a magnet. Okay, now, what Ampere thought was happening in that case was there were little particles. Well, Coulomb was the first to have this idea, if you remember. He thought there were little particles, magnetic particles in effect, that this magnet was made up of little tiny magnets, various orientations. And then, so they're all over the place at pointing in different directions in the normal case of just unmagnetized iron. But what happens when you put them next to, say, some permanent magnet is they tend to line up, right? So that's how you actually magnetize a piece of iron. And you end up giving it, a lot of these little magnetic particles now are all lined up such that, say, this becomes the North Pole and this becomes the South Pole. Now, when people had just been doing this with, magnetized rocks, lodestones, they had been able to line up, some of these particles, basically. But they weren't lining up all that many of them. And what happened when people found this connection between electricity and magnetism, and instead of just bringing a lodestone, near this piece of iron to magnetize it, they wrapped coils around this bar of iron and sent a strong current through those coils. They were able to produce in this bar of iron, very strong magnetic forces that really would line up all of these magnetic particles in the iron. And so you end up with a very, very strong magnet because you're actually using all that magnetism in the iron rather than just a part of it. Drew.
If you took the coiled wires off, would it still be strong magnet, or would it go back to a normal?
Well, after you've magnetized it with the coil, you could take the coil off, and as long as you didn't heat it up and so the particles become disoriented again, they would stay in that Yes, largely in that orientation. So you could make, even after you took the coil away, you would still have a stronger magnet than you would ever have, say, with a lodestone. Nick.
But sometimes if you like put a magnet up to a paper clip, the paper clip kind of becomes a magnet for about a minute and then it dies away.
Oh, it becomes magnetized for a short time. I mean, well, it's never strongly magnetized, right? It is just barely enough to like hang. Yeah, I'm not sure. I mean, most paper clips, of course, are not. I mean, they're not made of iron. So I think in that case, I'd have to know what the paper clip was made out of to really give you a good answer. But what I suspect is that it's not this same kind of effect where you have all of these magnetized particles that can line up like it is in iron. There's other materials that can be, in certain circumstances, induced to have a temporary magnetic effect, but as soon as you draw the magnet away, they go back to their normal state. But it's a different kind of material than iron is. Okay. So basically, by using coils to create a much stronger magnetic force through this bar of iron, you can make a much, much stronger magnet. And so that's why Joseph Henry ended up with this 90-pound horseshoe magnet with 9 coils wrapped around it that could lift 2,000 pounds. Okay. Now, so far, in terms of what we've seen Faraday do, we've seen him demonstrate the basic laws that were discovered by Ampere, right? I mean, Ampere showed how currents produce magnetic forces and therefore act on magnets, how magnets can interact with currents and exert forces on currents, and how those forces go around in circles. So Faraday just came up with that clever rotation experiment to demonstrate exactly how that works. And he invented the galvanometer. We saw the first simple electric motor. But all of these devices, they all work on the basic principles that were discovered by Ampere. So Faraday hasn't discovered anything brand new yet. But he will. And I want to start to tell you about that. But the first new thing that Faraday comes up with is not a brand new law, but a certain new perspective that he takes on what's going on physically in the various situations that we've seen. So let's just call this Faraday's idea of fields. Now, I'm sure all of you have noticed that I've slipped probably a dozen times so far in this class. Rather than saying magnetic forces, talking about magnetic fields. But I haven't told you what exactly a field is. So I've been trying not to use this idea and having difficulty. So now I want to try to explain to you what the idea is and why it's necessary to really think clearly about the sorts of phenomenon that we've seen so far. Faraday makes a distinction here between. See, I've been talking about magnetic forces. Let's say we have, consider the case that we've talked about before, where we have two wires. And let's say we have two parallel wires, and as I've drawn them on the board, the current's going up, okay, in both cases. Now, consider the force on this wire. Okay, what direction is it in, by the way? Sorry.
It's being attracted towards the other.
Yeah, it's being attracted. How do we know that? Well, Troy, go through it.
Well, since you use the first right-hand rule, and then you know that.
Okay, so the force on this wire is due to this wire. Stick your thumb in the direction of that current. You bend it around. Okay, so there's something going into the board here. Now, I've been calling it the magnetic force, right? Now, what did I really mean by that? It's not the force on this wire, right? It's the force that would be experienced by a magnetic north pole in that location. All right? And that's the way I've explained it. But, of course, a force, strictly speaking, is always a force on an object. So it's kind of peculiar, the way I've been talking, right? That I've been talking about a magnetic force here, but in fact there's no object there being pushed in that direction, which makes for an awkward way of talking. Now, Faraday saw that this was an awkward way of not only talking about these effects, but even trying to think about them. There seemed to be an idea that was missing here. And he supplied the idea. Rather than talking about a magnetic force at this location, Faraday calls it a magnetic field. Okay? And what Faraday says is that anytime you have an object let's say you have a body 2 here being acted on by body 1. Okay, now the simplest case that we learned about last year was if these bodies are masses. Okay, so there's just a gravitational attraction between them. Okay, so you have a mass here and a mass here. Well, the attractive force between them is given by the gravitational equation, where r is just the distance between them, right? But Faraday, the way he thinks of this is, well, anytime there's a force on this body here due to some distant body, you can think of it as force on body equals some property of the body multiplied by, the force field at that location of the body. So let's just make that explicit. So in the case of gravitation, it's the relevant property of the body is its mass, right? I mean, if you double the mass, you'll double the force. So the force is proportional to this property of the body, but then there's something about that location of space that place that the body is in, that Faraday, in this case, is going to call the gravitational field. Now that gravitational field at this location is created by this mass over here. Okay, this is sounding complicated. It's really an easy idea. We've been talking about forces from the beginning, last year, and then we've examined electrical forces, magnetic forces, and in all those cases that we've talked about, we've always had some body that was being acted on by no visible means, right? It's not a push or a pull. It's some distant body with mass or with electric charge or a current or a magnet at some distant location that is exerting a force on this body. And the way that body responds, we've seen, is proportional to its mass, if it's a gravitational force, or its charge, if it's an electrical force, or its current, if it's a magnetic force acting on a current. But it's also directly proportional to something that doesn't depend on this body at all, that just depends on the other body that's creating the force. Okay, that's the field. See, this number 1 here is doing something over here at this location, right? Otherwise it wouldn't be making this body move. And so what Faraday says is, well, body 1 has created a field that pervades all the space around it and has a certain direction and magnitude at this location. And that is what is acting on body 2 here. Okay, does that sound like gibberish, or does that make sense? I'm not sure what... I know this is a little more abstract than the experiments that we usually are talking about, but you can... it really does have a value, particularly when you get to this stage. Now, for a long time, like in gravitation, you could just talk about the force on body 2 here, and physicists really didn't need to introduce this idea of fields, or at least it wasn't as crucial, because it was just an attractive force, and the force and the field are in the same direction in this case. In the case of gravitation, the case of static electricity. But here, when you get to the kinds of magnetic fields that are created by currents, we have, for the first time, this funny situation where the the magnetic field created by this wire is into the board at this other wire, right? But that's not the direction of the force on the wire. The direction of the force on the wire, we've seen, you have to cross the current into that magnetic field direction in order to get the force on the wire. So here we've actually got a case where the relevant field direction is different than the direction of the force on the object. And that actually really forced Faraday to make this distinction between forces and fields. Okay. Now, so Faraday actually has a way of thinking physically about what is going on in a situation like this that prior scientists didn't have. He actually thinks in terms of these circulating field lines. And I mean, even if you only have one wire here, as soon as you have a current through it, it's not exerting any force on objects around it, but Faraday's thinking in terms of these swirling lines of magnetic force, of magnetic field. And Faraday actually came up with clever ways of visualizing this using iron filings. I don't know if you've ever seen experiments like this, but if you take say a wire with a strong current through it, and you poke a hole in a piece of paper, and you put that wire through your piece of paper, and you have iron filings sprinkled on that piece of paper that are sort of free to, you can shake them, and they're free to sort of move around. Well, you'll end up with, actually I should have brought pictures for you today. I'll do that next time we meet, next Monday. But you'll see all these little slivers of iron lining up with the field lines. So if you look down at your piece of paper, let's say you're, so we're looking down now, so the current is coming out of the board. And we know from Ampere's law that these magnetic field lines that Faraday talks about should be going around counterclockwise in that case, right? Well, you'll see all these little iron filings. Lining up. I mean, you'll see them swirling around in circles. And you can do the same thing if you put a bar magnet down on a sheet of paper with iron filings on it, and shake them around so they're free to move and line up with the field lines. You'll see something. You see these iron filings going around in these patterns, just mapping out these the direction of these magnetic forces, the direction of the magnetic field. And this doesn't even have to be a bar magnet. What if you did? What if you got rid of your bar magnet and had a coil of wire here that you put a current through? You'd get the same pattern. yeah, horseshoe magnet, you would get, I mean, if you had, say, oh, I didn't do that quite right. Yeah. Let me see. Let's start over. Let's say North Pole, South Pole. What would you see? Yeah.
There would just be straight lines between them.
Yeah, I mean, what you'd see, the little iron filings right between would just like line up, okay? And then as you moved out, you know, it would be more like this. Yeah, you can see, you can use these little iron filings just to map out, to actually see the direction of these magnetic fields. Nick.
But why wouldn't the iron filings just stick to the magnet?
Oh, I mean, yeah, if they're, you're right that if the magnetic field was strong enough, in this case, you would just see them piling up on the poles. So you'd have to prevent that. If, for example, you had them on a piece of paper that you laid over this this magnet, then you would see something like the pattern that I just drew. Okay, so Faraday now, he thinks in terms of these field lines, and then he uses Ampere's, you know, rules, of course, to figure out the forces in any given case. But he's, you know, he doesn't have to think about it in that kind of awkward way that I've been explaining it to you, talking about, you know, magnetic forces when there's no real North Pole there to respond to that force, and then talking about the magnetic force versus the force on the actual wire. You know, we can just talk about the magnetic field, and then understand that if we're talking about the force on a current-carrying wire, that we can figure that out using Ampere's rule. So this just gives you a by visualizing these field lines, it really helps you think and get clearer about what is physically going on. And there is something physically going on, even though we can't see it. I mean, obviously, in the case of gravitational forces, we don't see the physical means by which bodies are attracted. And we don't, of course, for electrical forces or these magnetic forces. But we don't see air either, and we don't see sound waves. But you know, we've got a ton of evidence that there is such a thing as air, there is such a thing as sound waves, because we see their effects. And it's the same thing here. Fields are as physically real as air and sound waves are. We just don't see them. But we've seen a lot of their effects so far, right? Okay, now that was a crucial new idea that Faraday had, but of course it's not a new, it's not like the discovery of a new law. But he does that too. So that's the next major innovation that Faraday makes in this field, shall we say. So let me tell you about Faraday's discovery of a new law, later I'll tell you a name for this law, but I don't want to give it away now. Now we've seen that a current can, in effect, produce a magnet, right? I mean, if you take a coil of wire, it acts just like a bar magnet, right? So you can use an electric current to, in effect, create a magnet. Well, that led Faraday to ask, can you guess? Yeah, Evan.
Can you use a magnet to create an electric current?
Exactly. Exactly. Can you turn this thing around? If you can take a current and, in effect, create a magnet, can you take a magnet and somehow create a current? Now, the only way that we've seen how to make a current so far is how?
With a battery and a wire?
Yeah, I mean, if you don't have any dead frogs around, you're pretty much stuck using batteries. So that's it. I mean, the only way we know of to create an electric current is to have these, say, silver and zinc plates separated by some salt or acid solution, you know, to make a battery that creates the electric current. But Faraday has the idea, maybe he can somehow use a magnet, use magnetism, to actually create electric current. So one day in 1822, Faraday's making up his to-do list. I don't know whether any of you ever get organized like that and makes up things to do on your list. And most people have things like go to grocery store, you know, work out at the gym. Well, on Faraday's list, he put, quote, convert magnetism into electricity. So he, that was on his to-do list as early as 1822. Now, he did make an effort to do it, but nothing he tried worked. He tried, you know, putting really strong magnets up near wires and seeing whether he could measure any current. You know, he's got his galvanometer now, so he can, any current he produces in a wire, he can measure that current, and so he knows there's a current in the wire. Yes?
Was it Faraday or Ampere who had the who invented the galvanometer?
Oh, I mentioned this morning that both of them did independently, actually. So I think Ampere was the one that actually named it, the galvanometer. Selah.
When he tried doing that, like, did he only put one magnet up to his wire, or did he like put a bunch all around it or something?
Well, I think he tried, I mean, he wasn't sure what he had to do in order to try and produce an electric current. So he tried lots of different things, and none of them worked. And this went on for years. But he still kept in his mind the idea, somehow he still suspected that magnets could be used to create electric currents. He just hadn't stumbled on the right method yet. And let me cut right to the first successful experiment that he did and show you exactly how he set it up. And we'll see that there is something new here that threw people off, and this is why it took forever to discover this. And people like Faraday asked this question, I said, as early as 1822. He doesn't actually make the discovery I'm about to tell you about until 1831. So 9 years go by. Okay. But in 1831, he tries the following setup. He's got a iron ring. Okay, now he takes a wire and wraps it around this ring and hooks it up to a battery. Or, well, he's got a battery that he can hook it up to. Okay, he doesn't hook it up yet. Let me finish my drawing before we hook it up. On the other side, he's got something similar. Except on this side, he's got a galvanometer.
Hooked up to the galvanometer.
Yeah. Okay, can you see what Faraday's trying to do here? He's going to send a current through this wire, okay, when he hooks up his battery. Now let's say that, I don't know, this is the positive end of the battery, that's the negative. So we've got a current going in this direction. So it would be going through this coil counterclockwise. Okay, now you can use your Ampere right-hand rule to show that that will create a magnetic field in that direction, okay, into the bottom of the coil and out the top. Now, that magnetic field is causing all these iron particles to line up in that direction. Okay, well, it's going to cause them to line up all around this ring. So as soon as Faraday hooks up his battery here, the upshot is that he's causing a magnetic field through this other coil. Yes?
But how would he know that it's just not that the wire is going through the iron ring into the other side?
Oh, he has this insulated, so there's no contact between his wire here, the metal in his wire, and the iron ring. Yeah, that's absolutely, yeah, good question.
But
Yeah.
is the other coil insulated?
Yeah, that coil's insulated as well. Okay, so there's no electrical, there's no path by which the electricity here can get over here.
So then
Yes.
how is it possible that if the iron ring does generate a little bit of electricity or something, that it gets to the galvanometer?
Oh.
How will the galvanometer measure anything?
Oh, well, I'm just getting to that. But it's not that, I mean, the situation is set up so that the electricity being created by this battery is, there's no way it can get over into this wire. So forget about that. That's not going to be the cause. If we see any current over here, it's not going to be caused in any direct way by this battery. Now, what Faraday's looking for is, I mean, what he's created is a sudden magnetic field going through this coil, right? I mean, as soon as he flips on his battery, he creates this magnetic field in the iron ring that wasn't there before. So he suddenly changed the magnetic field through this coil. And what he sees is, when he flips the battery on, he sees the galvanometer deflect suddenly. There's a surge of current in this wire. And then after the battery's been on for just a little while, the current goes back to zero. Strange, huh? Now, and that happens every time. If he connects his battery, the moment he connects it, he sees a deflection of the galvanometer needle showing a current here. And if he leaves it connected for a while, it doesn't, the current goes back to zero. Then he disconnects it, and he sees a little deflection where there's more current, and connects it again. So basically, what Faraday has discovered here is that not only do you need a magnetic field through this coil to create a current, but you need a changing magnetic field. If the magnetic field is just steady, it doesn't cause any current, which is exactly why nobody discovered this for so long. If the magnetic field suddenly changes, it causes a current surge. Nick.
I know there's a way, like, with the, I think there's another way eventually, but with this setup, is it possible to at least just keep it?
Oh, well, there are ways, this will be tremendously applied, because people will figure out a way to continuously change the magnetic field, and so to continuously cause current. I mean, that's exactly what they do at Hoover Dam that gives us electric lights. I'm already over time, so I'll have to answer your question. Okay, that's it for today.